All right, well, welcome everybody. Welcome back to our last seminar of the year. Um, I hope that everyone is doing okay with your finals and last minute letters of recommendation and applications. I know this is a very busy time for everyone, so thanks for coming. I'm very excited to introduce our speaker today, David Rosario, who is a senior lecturer at Newcastle. David is one of those people who are very visible because every time that you go to a conference and he makes a comment or a question, it's always like something very insightful. So even from the time, I think from the time he was a grad student, I've sort of been following his career. And so I'm very excited that he's here with us today. David got his PhD from the University of Virginia, and then he went on to get a postdoc at the University of California, Santa Cruz. From there, he moved to Europe, and he was at MPE in Germany. And by the way, I was invited to give a talk there one time, and I was super looking forward to seeing David, and then he had just moved to England. So no, actually, he went to Durham, yeah. And then he was there for a few years. And then just recently, he moved to Newcastle, where he's a senior lecturer. I think David has worked with every space telescope, at least the ones with slightly longer wavelengths. He's done work with the Hubble and the Kendall survey, and he's worked with Herschel and ALMA. I mean, ALMA is not in space, but
might as well be.
So I'm hoping that he will tell us about his upcoming work with JWST. I mean, I know he will. So anyways, so something very interesting that I just found out about David is that he was pretty busy during a good portion of the pandemic, filming with the BBC and with PBS. And there is the, so it's a PBS series that came out, I believe, Universe Unveiled or
Revealed.
Correct. Revealed, okay. Yeah. So I'm excited. I always show clips of documentaries in my classes. So I'm actually excited to watch this one and to get some clips for class. So I encourage you to look it up, and I already have the link marked in my webpage, and I'm going to be watching them during this winter break, if they're available. I think they're available, right?
Yeah, they should be available on streaming now through PBS. Yeah, anyone in the US should be able to watch it.
Perfect. All right. So it's my great pleasure to introduce David, and thank you for coming.
Thank you, Gabby. That was a wonderful introduction. I feel very happy. I feel I'm tingling a little bit for all of the praise. Thank you. I'm going to be telling you about sort of a constant theme in my research, which is trying to understand active galaxies, AGN, in the context using the tracers of the cold universe. So this would be, gas and dust in galaxies. And, just to get a broad sense of what I'm talking about, cold gas and its, its constant namesake companion, minion, whatever you want to call it, dust, are, essential components of galaxies, right? They define the visible nature of galaxies. They dominate much of its dynamic processes in galaxies, such as star formation. And, as this sort of image is supposed to represent, the nature of gas and dust plays a big role in our understanding of AGN. Now, I'll mention that this is actually supposed to be an image of a brown dwarf, but it looks so much like an AGN that I thought it'd be reminiscent for anyone here in this meeting. And, we have this notion of a torus, and our understanding of the visible nature of AGN is strongly determined by this dusty structure, right? So cold gas and dust play a key role in our understanding of AGN and galaxies. So how do we study these components? For a long time, for the good fraction of the last decade, the state of the art was the Herschel Space Telescope. You know, there are other infrared telescopes before it, but Herschel in many ways revolutionized the field. And the reason it did that was because it had a significant survey component. The Herschel was a fast telescope. It could cover large areas of sky and give you large samples of the cosmos at depths that were unprecedented in the far infrared. So this is from 70 to 500 microns, which is approximately where Herschel covered. And there's a huge legacy for Herschel data. And a lot of my earlier work that I'm going to start off with is based on Herschel. But the new kid on the block is ALMA. And the reason that ALMA is so much better than Herschel in certain ways is because it looks at colder dust, right? So ALMA is a millimeter, sub-millimeter wave observatory. So if you're used to thinking of single telescopes like Herschel, ALMA is a step ahead because it's an interferometer, you know, classically the kind of things that radio astronomers would have used, but because it works at the wavelengths in the millimeter and sub-millimeter regime, it's sensitive to dust emission as well as other components, of course. And I think another very useful component that comes from ALMA is its sensitivity to molecular gas. These transitions from molecules in cold gas pop up in the sub-millimeter bands, and this is what ALMA picks up. Now, here's a fun fact that is worth keeping in mind. Even though we love JWST, right? JWST also being an infrared telescope, one might imagine, you know, much more sensitive than ALMA. It's going to revolutionize star formation studies, etc. It turns out that ALMA is still going to be the premier instrument to study coal dust emission, even in the era of JWST. And just to give you a sense of that, basically the reason is because with ALMA, you're in the Rayleigh-Jeans part of the dust emission curve in galaxies. So as you look towards higher redshifts, you actually become more sensitive to the dust in a relative fashion. This is, you know, shown in this right-hand panel here. This is just the star formation rate sensitivity as a function of redshift for some nominal surveys, right? So it's just you know, sort of characteristic surveys that people might attempt to do with JWST and with ALMA. And you'll see that once you get beyond redshifts of 3, ALMA, you know, ALMA has almost a uniform sensitivity to star formation or to dust emission across redshift, whereas JWST quickly loses out of steam once you get beyond redshifts of 2. And all of these are significantly better than Herschel, right? So things are great. JWST is going to give us something. ALMA will give us something else, and we'll get this lovely, deep understanding of star formation across the universe. So how is it relevant to AGN? Why is this cold stuff valuable when we're studying active galaxies? The main reason is sort of summarized in this SED here. This is a well-known nearby Seyfert galaxy, NGC 5548, extremely well studied. It's a sort of poster child for you know, the reverberation mapping studies that you've seen in some of the previous talks in this series, where people try to understand, you know, really hone in on the black hole mass for these systems. So 5548, you know, is a type 1 AGN, so you have accretion disk emission. It's got a substantial host galaxy, so you see stellar emission. There is a torus in it, and so you see this hot AGN dust emission. But it's only when you go to the longest wavelengths that you get a clean view of the dust emission coming from the galaxy. And this dust emission is cold. It's primarily produced by star formation. And so it's only once you go into the far infrared that you can accurately measure things like star formation in this particular galaxy. So the far infrared and sub-millimeter bands are crucial, especially at higher redshifts, to try to track this star formation down. And so let's think about how we put this all into context. One of the crucial astrophysical results that we always seem to you know, have in all of the introductions of our AGN papers is the correlation between black hole mass and galaxy mass. You know, it's a binding result in astrophysics right now, and we still don't fully understand it. It turns out that there's many ways to produce this relationship, but the main tenet of all of those is that the black hole and the galaxy sort of grow together, right? Do they grow side by side in lockstep, or is it more of a statistical question? It's still somewhat open, but I'm going to go with my side of this argument. I'm going to say that the majority of black hole growth happens in what I call an unsynchronized fashion. And this means that there isn't a specific timescale relationship between star formation, the star formation growth of a galaxy, and the black hole growth through an AGN. The connection does exist, however, but it's in a more loosely defined way, and it's primarily through the supply of gas. So here's a schematic that's supposed to represent what I'm talking about. The key element here, however, is that star formation across a galaxy, so its average growth rate, changes slowly with characteristic timescales of 100 million years or longer, whereas AGN very rapidly. So the characteristic variational timescale for an AGN is just 1 million years. In 1 million years, a particular black hole could go from being completely quiescent to producing a quasar. That would be the idea. And so here's just a simulation where you have this sort of slow change in galaxy growth. And on top of that, I've superimposed a much faster variation because of an AGN. So this is much faster variation from black hole growth. And remember that for most of the sort of black hole growth lifetime, you can't detect an AGN. An AGN is only detectable if you're above a certain threshold, right? So all these high points represent the age-specific phases in which you might capture an AGN. So that's represented here. Here, for example, this particular blue galaxy has a large amount of star formation, and the black hole is quiescent, but a short time later, the black hole is visible as a spike, and then you see an AGN in the center. Similarly, when the star formation has dropped. Now, the good thing to keep in mind is that you can detect AGN even if the star formation is high or if the star formation is low. What is crucial here is that the averaged growth tracks the star formation growth. So this would, in combination, this would produce a relationship between black hole mass and galaxy mass. But you need to average over a long period of time in order to do that. You don't do that when you study AGN as individual events. So it's a bit complicated, but this simulation, recent simulation by Daniel Angeles Alcazar, brings it all into focus. So what you're seeing here is actually a simulation of gas inflow into a growing black hole. And we've now moved from galaxy scales down to the inner 100 parsecs or so. Tons of gas is falling into this black hole, right? So it's growing at a pretty substantial rate, but the variational timescale for that growth is much shorter than the variational timescale for the growth of the galaxy as a whole. So when you look at the galaxy with the same time resolution, you see almost no change in the galaxy, whereas the black hole is furiously going through growth phases. So that's the view that you should keep in mind when thinking about how your particular AGN relates to star formation. And to me, the evidence that most coevolution is unsynchronized is quite simple. We don't find an obvious difference in the star formation rates, average star formation rates of weak AGN, Seyferts, or the most luminous AGN, quasars, right? If you go in, so for example, these are some results. Ooh, what just happened? Did it? Oh, sorry about that. It looks like my keynote died on me. Just give me a second. Let's go to this one here. Sorry about that. Computers, right? Am I right? There we go. Okay. So hopefully this continues without any issues. So we don't find any real evidence for a strong trend between average star formation in galaxies in low luminosity AGN or high luminosity AGN. These are some of the results that I put out in 2012. There have been plenty of studies that have shown this. However, if you twist things around, if you don't look at average star formation, but instead look at all star-forming galaxies and look at the average AGN power coming from, then there's a strong correlation. So this is the result from Ivan Del Vecchio's work. Again, there's a number of studies done something similar. If you just look at the large star-forming galaxy sample and look at the average star formation rate as a function of the average AGN luminosity as a function of star formation, there's a strong relationship. And this can be fully explained if you average, depending on whether you average in this quantity or average in this quantity. And so to me, this is sort of some of the best evidence we have that the majority of black hole growth is unsynchronized. One might ask, okay, how about if you look at the most luminous AGN, right? Maybe those Seyferts don't matter. They're not most black hole growth doesn't happen in the Seyfert phase. It happens in the phase that we define as quasars or quasi-stellar objects, QSOs. What if you look at the quasars themselves? Are they in a unique phase, right? Maybe we should be concentrating on those objects when we're trying to understand the total growth of a galaxy. And so this was some of the earliest work that I did with Herschel on the nature of star formation in quasar host galaxies. And this was in the cosmos field. At that point, it was the largest study of type 1 AGN, as we call them, quasars, objects with broad lines in their spectra. And the approach we took was, because of the limitations of Herschel, rather than individually studying objects, all we could do was sort of stack their fine Fred properties. So we made grids, for example, in bolometric luminosity. This is just bolometric luminosity versus redshift. These lines are supposed to represent limits. Don't worry about them for the moment. You see that we cover a broad range in bolometric luminosity, going all the way to about a few times 10 to the 46. So these are relatively powerful quasars, not the most powerful in the universe because we're looking at a small field, but they're classic quasars in many ways. Broad range in black hole mass and accretion rate, for example, and we binned them and essentially looked at their mean star formation rates. And this was a little surprising back then, and this has been repeated a few times as well. The surprising thing was, I just told you a couple of slides back that when you look at average star formation rate, that's what we see here, versus say bolometric luminosity, which we see here, there shouldn't be a trend. And yet for these quasars, we did find a trend. So for example, just look at the red dots. That's just a particular redshift bin. We found a definite increase of the star formation rate as a function of bolometric luminosity, which we didn't understand till we thought of quasars as not as a uniform monolithic sample, but actually being within galaxies where, for example, things like black hole mass correlate with stellar mass. So what we did was we came up with a model that considered quasars to be normal star-forming galaxies, and then predicted, based on their black hole mass and bolometric luminosity, how much far-infrared emission they would produce. And sure enough, that's what this model is supposed to represent here. These different shaded regions are actually the model I'm talking about. It worked remarkably well. Essentially, quasars could be explained as normal star-forming host galaxies, where, when I say normal, I mean that they're on this so-called main sequence of star formation. And much of these trends are not because there is a synchronization in star formation with AGN luminosity, but because more luminous quasars are simply in more massive galaxies. It's as simple as that. The average luminous quasar is in a different kind of galaxy from the average low luminosity quasar or low luminosity AGN. And that explains many of these trends really well. And it's an important bias that has to be kept in mind. When you look at things like AGN luminosity, you are pre-selecting different phases in some sense. The reason is because most luminous AGN can only be sustained when you have a massive black hole with a lot of gas. It's essentially that. And so you're not going to find many of them. You're going to pre-select these things when you look at the most luminous system. So it's an important bias that we uncovered in these studies. And we always try to keep it in mind when modeling the nature of AGN hosts now. So it tells us something about this how you interpret evidence for coevolution. Right. So I've tried to make a case, not necessarily very well because it's a complicated thing, but just give you my viewpoint there, which is that coevolution is unsynchronized. But what about what I call synchronized coevolution? And when so again, I'll define this term. When I say something is synchronized, I mean that the major phase of black hole growth happens in lockstep, or a short time, either at the same time or maybe with a short delay with respect to a major growth in the galaxy, a big burst in star formation, right? So major mergers are a well-known way to enhance the growth of galaxies and of black holes in one go. And here, for example, is evidence of this. These are actually tracks from really well-known major merger simulations. This is the work of Phil Hopkins and TJ Cox and others, which shows how star formation and AGN luminosity track each other in these simulations. So this is just time spent in different points on this on the space here of star formation rate versus AGN luminosity. And he said that there's expected relationship between the two. So this is a synchronized kind of relationship, a synchronized black hole growth. So I'm going to tell you about more recent work where we've tried to zoom in on a particular population where we think that this sort of synchronized coevolution might be occurring. Excuse me. This population are so-called red quasars. Red quasars have been studied for a long time now. They have a couple of decades of history, if I remember my literature review well. The archetypal red quasar is in fact a nearby ULERG called Markarian 231. This is a well-known object. You can see a bright point source in the center, which is red. But the host galaxy is in this really complicated major merger. So Markarian 231 has led our thinking about red quasars even at higher redshifts. And people like Glickman and Manda Banerjee and a number of others have come up with effective ways to select red quasars from large surveys. And ALAT, for example, has found that a number of these objects, when studied with the Hubble Space Telescope, do show evidence for major mergers or some sort of disturbance in operation. So there's an abiding result that if you select things that are red, but bright point sources, so quasars that are reddened for some reason, you might be finding cases where you are enshrouded by dust and maybe finding a particular phase in black hole growth. So let me just show you what this is in this particular schematic. This is a schematic put together by one of our students for her work, which I'll come to later. The idea is that merging galaxies, when they're gas rich, for example, produce these massive starbursts, similar to what you see for the host of Markarian 231. And a strong starburst is associated with a dense gas-rich phase in the center of the galaxy that fuels a quasar. But the quasar in the beginning, for who knows how long, maybe a million years, maybe less, is so enshrouded that you can't see it, even though it's pumping out energy into the inner kiloparsec of this structure. It's not visible because the dust blocks it out. However, because of all this energy pumped into a small volume, you very quickly blow away the enshrouding dust and gas. And for a short period of time, you remain red because there's still a little bit of dust along the line of sight to influence your view of quasars. The quasar, however, abides while the dust goes away, and then you're left with a short-lived phase where the quasar is blue, short-lived but longer than the red phase, and then everything settles down to the merger remnant, which is an early type galaxy. At this point, you're done with all the dust and the gas, you've blown it all out, and you're left with something that's more red and dead. So this evolutionary model implies that the red quasar phase is associated with the starburst. It doesn't have to be at the exact same time, but it's much closer in time than, for example, a blue quasar. So that one would expect, for example, higher star formation rates in this. The other thing that you might expect is potentially some difference in the environment. It could be in the morphology, it could be in some other tracer of the galaxy besides dust, right? Besides something that's dependent on dust, right? Because we know that red quasars are dusty by definition, by selection. So we wanted to come up with a controlled approach towards selecting red quasars. The problem with a lot of earlier studies, delightful, beautifully done studies, but one thing that we always found lacking was we didn't understand the objects that they selected in comparison to the overall quasar sample. So there's quasars in the sky selected by various ways. How did these red quasars compare to normal quasars, right? So I'll remind everyone now, when I say quasars, I am really talking about the cream of the cream in terms of the AGN population. So when I say normal quasars, I don't mean normal AGN. I mean really powerful things that in which black holes are growing at a tremendous pace. So they are still really interesting, rare objects. However, I'm going to use the word normal quasar to mean the average quasar, the majority of quasars, which if you look at their spectra, this is an example of their spectra, these blue spectra here, that's what a normal quasar looks like, right? It has broad lines and is this continuum which keeps rising towards the ultraviolet. That's what a normal quasar looks like. This is what a reddened quasar looks like. It still has broad lines, right? And in fact, it looks very similar once you go to the rest frame optical. But as you go into the UV, you see this characteristic turnover, which is the consequence of dust obscuration. We're not talking about a large quantity of dust. If it was a large quantity, we wouldn't call them quasars. Actually, there's almost a bias there because you would not be dominated by their continuum emission or their broad lines. You would only see a host galaxy if it was really heavily obscured. So this is sort of a narrow space between unobscured quasars and the most heavily obscured AGN. Now, what we decided to do was keep it as simple as possible. We chose certain bands in the rest frame optical light, so just the STSS G and I bands, and said, you know what, let's just look at this color as a function of redshift, right? So here's what that color looks like as a function of redshift. These are all known quasars, spectroscopically identified quasars from the STSS DR14 catalog. And what you see here, these two colors, the blue and the red, represent the median color as a function of redshift. Okay, so this is redshift here, and this is G minus I color, and I'm choosing a redshift that doesn't go too high, because once you go too far into at higher redshifts, you start to be affected by the Lyman break, which comes into the G band. So you wouldn't want to go out to redshift 3 for this kind of selection. And then we don't go to really low redshifts because there's too few quasars. So there's this sort of sweet spot going all the way out to redshift 2-ish, 2.5. This is the median color as a function of redshift quasars. We do find, and this is known before, this big spread of quasars towards red colors, right? So we define the reddest 10% to be red quasars in our selection, as simple as that. So median quasars, we call them CQSOs or control quasars, and red quasars are QSOs. What we did find, however, and this is again also known from earlier work like Manda Banerjee's work here, is that even the reddest quasars look very similar to normal quasars in terms of their mid-infrared colors. So this is a WISE color diagram. W1 minus W2 is 3.6 to 4.5 micron differences in color, and this is 4.5 to 12 micron colors. And different objects occupy different parts of this diagram. And this is where quasars and Seyferts lie. And lo and behold, red quasars occupy a very same region in color space as normal quasars. So what this is telling us is even though they're reddened in the optical UV, they're actually not very different in their mid-infrared properties. And so we can use the mid-infrared property, and this is crucial. We can use the mid-infrared as a proxy for the actual luminosities. We couldn't do that with the optical because remember, they're reddened, right? So we can't use the optical luminosities as a measure of the actual power unless we de-redden them, which is a whole different ballgame. But we could use the mid-infrared, and that's what we did. We ended up using mid-infrared as a control tool. And we found something really weird when we studied these red quasars in this fashion. So here's just a summary of what we did. It turns out that the biggest difference we found between red and normal quasars was in the radio. This was a total surprise for us. we did a number of different studies, and this is the one that sort of popped out. When you look at the detection, as simple a thing as how often do you detect a red quasar in the radio, we found a factor of 3 difference between normal quasars and red quasars. And this was when we corrected for effects of luminosity, corrected for differences in redshift, all kinds of biases that we could correct for because of our selection strategy. This difference remained, and it's very pronounced. You know, a factor of 3 was you know, very easy to detect. So this was a study based on the first survey, and the main conclusion of this study was radio should not be affected by dust. By definition, in some sense, it is independent of the orientation of the quasar. So there is a fundamental difference in the radio properties of red quasars compared to blue quasars or normal quasars. And this was something that there were hints of this before, but I think we put it on much firmer footing. And we moved on since then. From first, we have explored using such things as the LOFAR radio surveys, which go a factor of 10 deeper equivalently than first, for example, and the result holds completely in the LOFAR domain. Now, you might say, okay, you know, detection rate, that's great. And what are we really learning from this? We took the trouble of not just looking at the detection rates of the sample, but we in fact examined their radio morphologies and looked at other factors in this sort of study. And so the other thing that really popped out, and this was the thing that really sort of got me, was when I saw this result, I said, oh, we're really onto something here. It's not just the difference in the detection rate. The objects that are more commonly found among red quasars are compact in the radio. Here's just an example of sort of little cutouts of radio images for quasars as a function of the sort of morphological type. So these things look like classical radio galaxies, you know, with 2 peaks, 2 lobes around the center. We found a bunch of objects which had extended structure with not necessarily these 2 lobes. And then everything else was either compact or too faint to determine. And you can see that all the classes of quasars, blue, red, you know, however you want to cut it, were very similar when you looked at extended radio sources, but there was a big difference in the percentage of red compact sources. And again, we established this clearly as well in using the LOFAR surveys at much lower luminosities. So this was astounding. You know, why compact? What's this telling us? It essentially is telling us the difference in what's producing this radio emission is not coming from, you know, many tens of kiloparsec scales, what we call supergalactic scales, but instead coming from something within the scale of the host galaxy, because it's some excess unresolved radio emission. And with these radio surveys, the resolution basically limits you to the size of the host galaxy, maybe slightly larger. We have followed this up actually with much deeper, much higher resolution radio imaging, and the same result holds essentially down to galaxy scales. And finally, just to convince you that something really interesting is happening, I define what's called radio loudness. So this is a term that people throw left and right all over. You know, what is a radio loud system? We have our own definition. And the reason we do it is because we believe we can use the mid-infrared luminosity as a measure of the bolometric power. So then the mid-infrared to radio luminosity is a measure of radio loudness. And this works better for red quasars because we can't trust the actual UV or optical luminosity for these objects because it's reddened. So we use the mid-infrared luminosity. And if you define it that way, red quasars, so this is a somewhat complicated part, but let me see if I can quickly tell you, because to me, it's quite astounding. What you see here in the y-axis is if you had a population of red quasars and blue or control quasars of the same size, right? Some fraction of them would be detected in the radio. It wouldn't be 100% because most quasars are not detected in the radio. But some fraction, say a radio detection rate of n, is the detectable fraction for the red quasars. And you can find a similar fraction for the blue quasars. The ratio between them is the enhancement in the radio detection rate, right? So it tells you whether red quasars are more likely to be detected in the radio than normal quasars. And so that, as a function of radio loudness, has a peak. So the most radio loud red quasars are as often are found at the same level as blue quasars, and the least radio loud systems also found at the same level. It's things that are at intermediate radio loudness that pop out. What does this mean? We don't know yet, actually. What is the specific nature of these radio intermediate objects? The fact that it goes down here, we think, is because once you go to these really low radio luminosities or radio loudnesses, you're in the star formation dominated regime. And star formation, for some reason, we think is not driving this result. We think that most of it is coming from some excess in the AGN power associated with red quasars. So let me build on this a little bit, because I've already talked to you about star formation, right? This is stuff that we've done for a long time. The simplest explanation for much of these, for the red quasar population that people have loved before, is that red quasars are associated with starbursts, right? So we decided to test this. We went to ALMA. We looked at a large sample of red and normal quasars controlled in the fashion that I just described, and we find no difference. The ALMA shows statistically no difference in the star formation rates of red and control quasars. They're all pretty high, commensurate with the fact that these are, massive star forming galaxies, as we have established before from previous work. But there's no statistical difference between the two. So this immediately puts paid to the fact that red quasars are all in starbursts. In fact, we think that the difference that we're finding in the radio properties are not driven by star formation at all. Instead, we think we're looking at quasar winds. Now, this is very strange. It's something completely different. I've been talking about growth and coevolution for a while now. Suddenly we move into this funny regime of winds. It came to us from left field, and I'll very quickly tell you about some of the exciting avenues that this is showing us. So quasar winds are well understood for a while because some fraction of quasars are known as broad absorption line quasars. So this is just an example of some sample spectra for a range of different broad absorption line quasars. I won't go into much detail here. A normal quasar is supposed to look a bit like this black line. If you have strong absorption, you get something like this green line. But about 10% of these objects also have very strong, very strange low ionization absorption. Those are called low BALs. That's the red and blue lines here. So these are a rare population that seem to show winds that we think extend to parsec scales. That's why they have low ionization properties. We still understand this population in detail, but for some reason, low BALs behave like red quasars in the radio. There's a remarkable similarity between these rare low BALs and a much more common population of red quasars. And so just an example here, this is balnicity index. Don't worry about what exactly is. It just measures the amount of absorption. So if you have a stronger wind, for example, or a more extensive wind, you have a higher balnicity index. And this is radio detection fraction, as I've shown you before. And you see that low BALs have a much higher radio detection fraction than normal BALs, and in fact, normal quasars as well. And this detection rate is about the same as red quasars from the first survey in this case. And then also low BALs have this high fraction of compact radio sources, higher than other samples. Now I'll tell you, there's so few low BALs that we don't have statistics for extended sources, but the compact difference is quite clear. So this is something that Dave Alexander is writing up right now. And we think that what we are seeing in the red quasars is not some sort of special star formation phase, but in fact, the presence of dusty winds. And so we think that there's a connection between dust raised by a wind and the reddening that you see in red quasars. So when you look at red quasars, you're actually looking along a line of sight that intersects a dusty wind rising out of the accretion structure. The nature of this wind, we don't understand. The extent to which this wind blows within the host galaxy, we still don't know. This is very hard to do because you need very high resolution to do it. So there's two alternatives, right? One is try to understand red quasars in more detail. And we'll certainly try to do that as best as we can. The other alternative is to try to understand dusty winds in nearby objects. And so finally, I can come to JWST because I've been trying to set you up here with a very interesting population where dusty winds might be driving their properties. We, however, already know from very nearby AGN that there is good evidence for these dusty winds. And so let me just show you what this paradigm is. It's a relatively new paradigm, but it's based on some very interesting studies. An example is this here, which kind of looks blobby. Some of you might have seen this result before. This is a reconstruction of what we think exists on parsec scales in one of our most well-known nearby AGN, which is the Circinus galaxy. The Circinus galaxy has been followed up. It's bright enough that you can follow it up using large infrared, mid-infrared interferometers, where you combine light from big telescopes into an optical interferometric system. This, for example, is done with the VLTI, the VLT interferometer. And what you see is, rather than most of the mid-infrared emission being concentrated in a disk or a torus, as you would have expected, remember this is parsec scales, there is a large fraction, about 50% of the fraction of the luminosity at 12 microns is coming from this polar structure. So this is the maser disk. That's what the maser disk is supposed to be. So this is where we think the accretion disk and torus should lie. But there's this thing that is extending perpendicular to it. And the interpretation of this, for example, from Sebastian Hoenig's recent review, is that there is a torus, but at the edges of the torus, when dust sublimates, the AGN is powerful enough to drive a dusty, conical, relatively conical outflow. And that's what you're seeing here in the mid-infrared. So this is optically thin emission from an outflow. And because it's optically thin, it has a higher emissivity, and therefore that's why it dominates in the mid-infrared. And people have done simulations of this. This is, for example, David Williamson's work from a couple of years. And notice the scales here. This is, it doesn't help that I haven't written it. This is supposed to be parsecs. So you can see that these winds can extend from that torus, which is tens of parsecs in size, to hundreds of parsecs. These winds could potentially be resolvable if you had the ability to actually look at this mid-infrared emission associated with these winds. This is incidentally, this is a mid-infrared simulation. So what you're seeing here is mid-infrared emission, not optical and not gas. This is actually what you'd expect if you were to look at this object in the mid-infrared. So we have taken heart from these simulations and proposed and gotten time with JWST to study 8 really well-known nearby AGN that have some prior evidence for extended dust emission. We don't know whether this dust emission is necessarily a polar wind. There is some evidence that it's aligned with ionization cones, but with JWST, we'll clarify this beautifully. So we're looking at this with 5 bands across the mid-infrared, and all of these objects, all these AGN, many of them are known and well-loved, have extensive ground-based adaptive optics, VLTI, Hubble imaging, ALMA spectroscopies, a whole bunch of different ancillary data sets that we can really understand these winds in detail. So that'll be 8 objects here. The same team, GATOS, which is a galaxy activity torus and outflow survey, is also managed to get time to study 6 nearby AGN with some overlap between the two, using the MIRI IFU in a mapping mode. So we'll be able to map essentially across these objects, get these beautiful, fully covered mid-infrared spectra across the entire central region, which we're trying to do outflow science as well as understanding the relation to extended polar dust. So there's a multifarious data set that we can use for many different things. I'll skip this. Don't worry about it. I think I'll end with no. You know, how much time do I have? What's the time? I don't have my.
Go ahead.
Okay. All right. So I'll just tell you why this is a useful thing. I've talked a lot about feeding, right? I've talked a lot about feeding black holes using, coal gas and the process of getting that gas to the center in many ways. But in reality, I think the most interesting aspect of AGN in terms of the galaxy population of the whole is the energy they put back. AGN are powerful engines for galaxy change, and these outflows that we are seeing here in dust, we already know that they extend to larger scales. So we are catching, in some sense, we're catching this sort of wind phase in a fashion where it's actually very easy for it to interact with the galaxy as a whole. So if we can understand these dusty winds in greater detail, we'll be able to get a very interesting angle on the energetics of these winds, which is crucial for a lot of broad galaxy studies. And I just want to highlight, this point that I was talking about, how important AGN are for galaxies. So here's just what always astounded me by looking at these. This is just a comparison of two versions of the same galaxy simulation. This is the famous Eagle simulation, one with and the other without AGN. Okay, that's the only difference. Everything else is the same. The volume's the same, the galaxy is the same, initial conditions are the same, star formation physics is the same, everything else is the same. Only in one of them, you don't allow black holes to form, right? So it's as simple, you don't see black holes. And that's a difference. This entire region of quenching massive galaxies is because of AGN. And AGN determine the width of the star formation mass relationship in galaxies. You don't need to have AGN in all these galaxies to do that. The AGN phase can be so short-lived that you detect AGN in only a tiny fraction of these galaxies, which is what we do. But the energy that those AGN put out can produce a profound effect in galaxy on the nature of the galaxy population and its evolution. And hopefully these dusty winds will offer a way to really tie down the amount of energy that's coming out from these AGN. So I'll summarize. Whoops, sorry about that. I'll summarize by saying that black hole growth is, I made a case, and we can debate that black hole growth I think is primarily unsynchronized in the sense that it's only average properties that correlate, but a particular black hole phase may not necessarily be tightly associated with the galaxy growth phase. And so much of the supermassive black hole scaling relations are therefore set by the supply of coal gas. It's mostly gas-rich systems which are massive, that can sustain the most strongly black hole growing phase, like quasars. And so I talked about red quasars and how they're very interesting. We don't think that they're mostly in starbursts. We think that the redness that we see in most red quasars is driven by dusty winds. And so these dusty winds may be a very interesting avenue towards exploring AGN feedback as a crucial phase in galaxy evolution. So I'll take questions, and I thank all of you for listening.
Thank you, David. That was a really good summary, a really great talk. So are there any questions? We have about 7 minutes before the hour.
See something in the chat.
Yeah, so okay.
It's Mitch, hey. Okay, so is asking if in the correlation of star formation with AGN luminosity, are all of the galaxies in that relationship of the same galaxy type and mass? You mentioned the most luminous AGN found in different galaxy types and low luminosity AGN. Right, so type is a tricky thing because we don't necessarily have a handle on things like the morphologies. We have tried our best using, this is work that I've done in candles, for example, to try to use morphological information as much as possible by looking at more obscured systems. And we don't find a big difference in the morphological type per se. There is a difference in the mass, however. And this is, I think, the abiding trend there, which is that more luminous AGN are associated with more massive galaxies. And that puts them in a sort of a different regime. And it's not necessarily because because they grow in lockstep or anything of that sort, is that you can't sustain these powerful AGN phases without having a massive black hole and a large supply of gas. So I think that would be the main reason why they tend to be in massive galaxies. Mass is a much slower growth process than an AGN phase, which is the basis of that understanding.
Great, that's very helpful. Thank you.
Sure.
Okay,
so I
go ahead.
see. I'm sorry, I don't see everyone yet because okay, there we go. So I see. I'll just go in order of what I see here. So Bina, what's your question?
Hi, thank you so much for a very interesting talk. Thank you. I just have a question about I think I can see the slide 28 where you talk about dusty winds, and this one and I think the 30th one as well, where you're showing some of the targets that you're going to study for these dusty winds. It seems like some of those probably co-align with the optical winds we see in these targets. And I think you mentioned that. And I was wondering if, if there's a correlation, like the optical winds are dragging these dusty clouds from the inner torus, or vice versa, like dusty winds are causing the optical outflows as we see in these targets. And what physical mechanism that is responsible for these? If that's the scenario, what could cause this?
Yeah, no, that's excellent question. So I think it's the simulation. Let me just talk from that simulation point of view. So for example, David Williamson's simulations here, what you see here in dust emission is a relatively biconical, relatively empty cone in the center. And there is a faster wind sheath essentially, which is blowing through the center. So, one could imagine that there is a faster optical wind surrounded by a cooler, maybe potentially slower dusty wind, which is launched from the torus. But again, I think it comes down to where exactly the acceleration is happening. So for example, with optical winds, you could have acceleration on larger scales driven by radiation pressure. We do know that dusty winds have to be launched by radiation pressure, but that has to happen at the edge of the torus, roughly here in the sublimation radius, because that's the only point in which the radiation pressure is significant enough, and the nature of the dust is particular enough that you can launch a substantial dusty wind. But optical winds might be launched at different scales. And we don't know for sure. With this JWST study, we'll have access to in some of the cases, we'll have access to mid-infrared tracers coming from spectroscopy, and we also have ground-based adaptive optics tracers for the optical winds themselves, emission line winds, for example. So hopefully we'll be able to put all of this in context for these objects because we have all this extensive ancillary data.
Yeah, perfect. Awesome. Thank you so much.
You're welcome.
That would be cool to see.
Hey, David, it's so nice to see you.
Nice to see you too.
It was a fantastic talk, as always.
Thank you.
So I wanted to pick up on this point very briefly, because I see we've only got 2 minutes left, that you articulated so nicely on your summary slide, which is, red quasars, we used to think about those as merger-driven activity, but now you think about them. So do these things really have to be mutually exclusive? So, I mean, maybe the morphology connection, I guess, with the red quasars was, you look at red quasar hosts, they're often disturbed. Maybe those are launching the dusty winds. And so you made the connection as well with the bowels. So is maybe to close the loop on this, to look at the morphology of the vowels and see whether those are also tend to be mergers, and if so, maybe that's the whole family you're looking at there.
Yeah, absolutely. Yeah, so that's what we're aiming to do here. So one of the complexities with red quasars is that what is causing the redness depends a little bit on redshift and luminosity. At low redshifts and lower luminosities, you can get red quasars by having a larger host galaxy, which in fact I think has biased some of the earlier studies in the sense that you're affected by the host, and that makes it look redder. I'm not saying that's all of them, but there are some which are some studies which have been affected by this. So the aim is we're using a uniform selection for the red quasars in a regime where we shouldn't be affected by all these biases. And the aim is to do an archival HST study as far as possible. We're working with Caroline Wilforth on this to try to see if something similar to what Eilat has done for her red quasars will give you similar results. We are also hoping to account for things like bolometric luminosity differences using our mid-infrared techniques as well, because I think that can play a bit of a role. As I said, the more bolometrically luminous you are, the more likely you are to be hosted by a massive host galaxy, and that kind of affects some of these things like merger signatures and things of that sort. So this is definitely a very important avenue that we're hoping to pursue.
Okay, thanks. Really envious of the JWST program, by the way. It's going to be awesome.
It's going to be fantastic.
Well, it's 10 a.m. But I would love it if you could stay for a few more minutes. I know Shobita has a question. I have another question too. So, but I mean, if people need to leave, thank you so much for coming. And Shobita, I don't know if you want to say something about the next seminar.
Oh, yeah, actually, this is the last seminar for the semester. And I think it's Michael, is he here? Who's giving the next seminar at the start of the semester. So it's posted on the schedule. And that's where you can find all the recordings and the abstracts. So join us next semester when we continue with the seminar series. And I don't know if Jeffrey wants to say anything to the bigger group.
Yeah, so if you're a student, undergrad or graduate student, please, if you want, if you have time, head over to the Discord channel and we'll get in there and we can discuss for a little while about the topics. And of course, David, once you're ready, and Gabby, of course, take David for as long as you want. I don't want to stretch anyone too far. But yeah, so feel free to move in there once you're ready. I'll be in there in a second.
All right. So